So in the previous video, we have defined the notion of arc length on a Riemannian manifold. Then using that, we define the notion of Riemannian distance given to a point P, Q. We define the distance between P and Q to just be the infimum of amongst the arc length of admissible curves starting from P and ending at Q. But remember, what started our discussion about length and distance? That was geodesics. Remember, we want geodesics to be the generalization of the notion of lines, but now for general Riemannian manifolds, we have defined geodesics to be curved with no acceleration, by which we mean these are curves whose velocity vector field has covariant derivative 0. Now, we want to give another characterization of it, which is that geodesics are locally length minimizing curves. First, we want to show that if a curve is length minimizing, then it must be a geodesic. What's a length minimizing curve? Well, a length minimizing curve is a curve whose length is equal to the distance between its endpoints. Or equivalently, a length minimizing curve from P to Q is a curve of shortest length amongst all the admissible curves from P to Q. Now, so why would a length minimizing curve have zero acceleration? The idea is that we want to view this length minimizing curve as a critical point of some arc length math on a family of curves. Then, using tools of calculus, we know how to find critical points, right? Using the first derivative, we will have something called the first variation formula, which relates this derivative with this acceleration, the covariant derivative of the velocity vector field of the curve. And from that, we'll be able to show that any length minimizing curve must be a geodesic. Alright, so that's the plan. Now let's formalize all of that. First of all, what do we mean by a family of curves? So we want to look at admissible families of curves. Intuitively, just as the name suggested, this is just a family of curves, of admissible curves. So each member of the family is an admissible curve on M. More formally, an admissible family of curve is a map, gamma, from a rectangle, right, inside M, so that for every choice of S here, so say S naught here, we get a corresponding admissible curve here, which is gamma S naught, a curve in the variable t. We call it the main curve. When we fix the variable t, each of these is called a transverse curve. Recall that for each of these curves here to be admissible, we need to be able to partition the interval AB in such a way that along that partition, this curve can be chopped off into regular pieces. Now the requirement for gamma, so gamma is an admissible family if on each of these squares, gamma restricted to the square is a smooth map. This means in particular that these transverse curves are smooth, right? Whereas these curves, these main curves are just piecewise regular. Now a variation of a curve gamma in M is an admissible family such that the member corresponding to 0, so the curve gamma 0 is actually little gamma. So gamma with s equals to 0 here is just a curve gamma. A variation is called proper if all the curves in this family, all the main curves have the same endpoints. So that's a variation. Now, how does this relate to the geodesics and length minimizing problem? Remember, we mentioned that the key in the proof that length minimizing curves are geodesic is the first variation formula. When we have a proper variation along gamma, we have a family of curves with the same starting point and end point. Right? For each s, we get a curve. Then we can look at the length of these curves, gamma s, and the length minimizing curves between these two endpoints must be a critical point then of this function. So the derivative of s, of this function with respect to s, must vanish there. So in other words, gamma is a length minimizing curve if and only if this derivative is 0. And from the first variation formula, we know that means this expression must be 0. And from that, we will be able to deduce that gamma must be a geodesic. So this will vanish. And from this part, we'll get that gamma is smooth, so it's indeed a geodesic. But to understand that, we need to understand these expressions, all of these notations, and where this comes from. For that, we'll need to introduce a notion of a vector field along this family gamma, and in particular a variation field, which we will introduce in the next video.